sei se é por causa do outro microfone.
Good morning, everybody. Welcome back to the second day of the school. Today we will start with the poster section. We will start with some presential participants first, and then we will start calling the posters from the online participants too. We have 5 presential participants today. The first one will be the student Alex Adriati from Professor Gamal, and he will talk about his poster now. Thank you.
Hello, everyone. Good morning. In my work, I studied the superfluidity properties in a beyond mean field approach. And we got one question here from Lucas Madeira. That is, could you explain in more detail the multi-configurational time-dependent hierarchy method for bosons? That is specifically the method I used. And the MSTDHB, which is the acronym to the multi-configurational method, tries to provide a more accurate description of the many particle state. And it does it by expanding the many particle state in the Fock basis, but truncating the individual particle state basis. So we have a finite set of individual particle states where we can expand the many particle state. And in this way, we have a controllable way to improve the accuracy of the results and to provide many body observables. So these are the underlying equations that arise from the MSTDHB method are a set of nonlinear partial differential equations coupled to usually a huge system of ordinary differential equation for the basis expansion coefficients. So, and there is another question. In which kind of situations is it useful? So I think the best case for the MSTDHB is when we have a small number of particles, since we afford freedom to explore strong interacting regions, and because we can have a larger basis to span a larger Hilbert space to express our many particle state. So this is the question left in the comments. Let me know if someone else have another question. All right.
No more questions? Oops. No more questions? Okay. I think you can then proceed with another students. Okay. Next one, Arnaud. Okay. Arnaud is not coming yet. Okay, you can then go with Arthur Rodrigues. Domingues, sorry. Arthur, please.
Hello everybody. My name is Arthur. I'm a master's student here in the Institute of Physics of San Carlos with Sergio Muniz. I'm studying quantum machine learning for quantum control. Here I've chosen to do a basic overview of quantum machine learning techniques. And here I have 2 questions. Actually, both are from one person. ML algorithms usually process a considerable amount of data. Thinking of this, are there efficient techniques in store a large amount of quantum data? I don't actually seen any techniques about storing a large amount of data. Mostly the computers that are being used to do this kind of computations, they have large storage space for being used to this kind of matters. So the answer is no. And yeah, the rest of the question is the hybrid computation the best alternative to this problem? Since they are not trying to do efficient storage techniques, this is not actually what they are using their human resources to research. And the second question is, are there completely quantum ML algorithms or just hybrid ones? So the algorithms, they're hybrid, they use in their quantum part, quantum algorithms. So the quantum part of the hybrid algorithms are actually quantum algorithms. So yes, there are, and mainly the way that they use these algorithms is via variational circuits. So yeah, I guess that's all the questions. Does anybody have any more questions? Okay.
Thank you, Arthur. Now we have our next speaker, Bruno. Oh, sorry. Sorry, Bruno. Come on.
Hi, Arthur. I did the question for you, and I just to want to be clear. So the quantum ML algorithms is you have the processing, quantum processing, and the storage is classical. So you have classical computers storage the data, and when you have to process the data, you have the quantum algorithms. Yeah. All right. That's it. Thank you.
Now you can find your homepage. Now we have Bruno that will make his presentation. Yes. Where is it? Just a minute, Bruno. My it's page 1. Acho que você está na 2. Go ahead. Go ahead, Bruno.
Hi everyone, my name is Bruno, and in my master degree project, I developed a Monte Carlo simulation to study the atomic dynamic in using a Monte Carlo using in the magneto-optical traps, narrow-line magneto-optical traps. And I have one question here about this from Caio. So, why it is so difficult to include the Doppler effect in the simulation? How well is the theory developed in this regime? I suppose that the theory you're mentioning does not include such effects as well, since the plots from theory and simulation match in this case. What is the current approach to this problem? So the theory include the Doppler effect specifically. So I include here in the tuning, when I talk about the radiation pressure force, I have here the Doppler effect included, but I think when Kyle is talking about the regimes, the Doppler regime is the usual regime, because in narrow-line magneto-optical traps, you have a falling, you have in the cloud, and this cloud is a lower position compared to the center, and this is a key point to apply the simulation, because you consider two independent level systems. So here you have a picture of the optical transitions. And usually you have a 4-level system, and you have to consider the assumption about independent 2-level systems. And this only can be done if you consider this approach when the cloud, the atomic cloud, fall down. And that's the reason the simulation doesn't work in this regime, the usual regime, because the cloud is in the center. And this is the center, the coherence effect of these optical transitions for level system is considerable. So the simulation only works in the other 2 regimen of narrow line magnetic optical traps, is the power broadening regimen and the quantum regimen, the regimen where the cloud is in a lower position compared to the center, right? More questions?
No more questions? Okay, if not, then thank you again, Bruno. Your next speaker will be Caio. Caio, please. Ok, Caio. Começa se apresentando, né?
Okay. Hello, everybody. My name is Kyle. I'm a PhD student. Oh, sorry. That's good. Hello, everybody. I'm a PhD student at the Federal University of São Carlos. When I submitted this poster, it was during my master's dissertation. And this work here, I've talked about the informational content of the wave function in the phase space approach. And I'm going straight to the questions, if there are any. Okay. What is the role of enharmonicities exponents greater or smaller than 2 for the increase and decreasing of the critical temperature? So one of the main results we obtained with this, let me just expand the poster here, from this enharmonic oscillator, which is this inverse square potential. We obtain these phase space currents, which do depend on the enharmonic parameter, but when we calculate any thermodynamic quantity like the partition function, we see that the harmonic oscillator is equivalent to the enharmonic oscillator, despite having these kind of vortices. Here we can see on the phase space profile, we can see these kind of vortices which are absent on the harmonic oscillator. But when you calculate the partition function and any thermodynamic quantity, you see that the 2 systems are equivalent. So I would say that if you consider a more realistic system with interaction between particles, we would find no dependence on the enharmonic parameter. But that is something that I've not calculated, actually. But that's my guess. But if you have any more questions, I might answer now. I don't know if there are more questions. Nope.
Any other questions? Okay, thank you, Caio.
Thank you.
Now we'll start calling our online participants. The first one will be Abel Beretti. Let me put his poster here. Okay, I think they will call him in minutes. Just waiting. I think they are connecting the Zoom. Okay. Abel, can you hear us? Hello?
I think there's a difficulty delay. Can you hear me now?
I can hear you, yes.
Okay, is it ready to start?
Oh, yes. If you want, Abel, please give just a brief introduction, please, about your work, your advisor, please.
Yeah, sure. So hi everyone, I'm Abel. I am a third-year PhD student at the University of Oxford in the group of Christopher Foote. And in our research, we mainly use radio frequency Dresde diabatic potentials to investigate various condensed matter phenomena. Recently, our work has been focused on understanding the Berzinski-Kosterlitz-Thouless phase transition in 2 dimensions, and we are investigating this phenomena in and out of equilibrium. So just to address some of the questions, I think 2 of you were asking about the trapping method. So we use, as I mentioned earlier, these multiple radio frequency diabatic potentials to trap atoms. These are essentially the bubble traps that Arnaldo talked about yesterday. The only difference is that we use 2 concentric bubble traps, and that's how we create a double web potential, and that's how we can have 2 pancake-like clouds. Then I think there was another question about the imaging protocol we use. So the way we image the atoms is through selectively repumping them before imaging with a thin light sheet. We derive this light sheet from a digital micromirror device, and normally the atoms would be in a dark state, so it's impossible to image them. We have to repump them, and by selectively repumping them, we can image only a narrow slice, and this allows us to extract the relative phase between the 2 clouds. Earlier experiments which did not use selective repumping used the contrast as a proxy for the phase correlations. However, directly accessing the phase gives us a more important information about the system. I think there's also one question, as I see, about how matter wave interferometry works in measuring the relative phases. Well, the idea is basically that if you have a 3-dimensional condensate, actually 2 of them, like this, top of each other, and if you release these 2 clouds, they will expand. And as they expand and overlap, they will form matter wave interference fringes. And let's say at this location here, the fringe phase will depend on the relative phase between the 2 clouds, as long as the time of flight is significantly smaller than the radial trapping period. And in our typical system, the radial trapping period is roughly 10 Hertz, while the time of flight duration is roughly 50 milliseconds. So we are in this limit, and therefore we are really probing the local phase in this system. In 2 dimensions, of course, you don't have a uniform phase, and therefore we see wavy fringes, and that's how we can extract the phase correlations from the system. Yeah, I believe I answered the questions about the trapping potential and the imaging method. There is a question about our last plot, the x and the y. So those x and the y are those variables that theorists use to simulate these systems, and those are parameters which are very difficult to measure directly by experiment. So just to give you a quick overview, x is related to the critical exponent eta, which describes how fast is the decay. In particular, x is 1 over 2 eta minus 2, so the x equals -2 line is the region of this plot where eta is very large, and therefore the decay is fast. And the y-axis is the so-called vortex fugacity, and that is proportional to the measured vortex density. So the higher up you are on the plot, the higher the vortex density is. Finally, if you could go to the first question asking about the quench protocol. The quench protocol is coherent splitting because initially we start in a single valve in which we produce a two-dimensional gas, and then we split into two. So the atom number halves, and we can use this quench to cross from the from the superfluid to the thermal phase of the BKT transition. Finally, actually, sorry, I have two questions. One from Jose, second question about interacting in time of flight. So these clouds, because they are confined very strongly along the Z direction, they expand rapidly. And when they interfere, the density is so low that we can virtually neglect the interactions. I was running some GP simulations, which were with and without interactions, and the difference is very, very, very small between them. About the absolute phase, no, there is no way to measure the absolute phase, because if you multiply your wave function with the global phase, physics won't change in your system. And also about controlling the relative phase. Well, what I can say is that we are splitting from a single cloud to two clouds in such a way that initially at time equals 0 after splitting, there is no relative phase between a constant relative phase between the two clouds, if that's what you mean by controlling the phase. Otherwise, controlling relative phases between two condensates is, for example, important for precision measurements, such as gravimetry. There it's extremely essential to control the relative phase everywhere. However, in our case, if there is a kind of global relative phase between the two clouds, which is the same throughout the whole cloud, we would just see it as a shift in the fringe pattern. But what we're interested in is how wavy that pattern is, so they are two completely different observables. And then finally, Lucas asked about the interaction. We do have a fixed interaction strength between the atoms. Experimentally, it is extremely difficult to vary the interactions between the atoms because we can't really use Feshbach resonance in our trap. That is because it is an all-magnetic trapping. And therefore, we can't really tune the value of the magnetic field independent from the trap, like in optical dipole traps or lattices. However, there is actually a way to control the interaction strength. That is because in 2 dimensions, the interaction strength is renormalized. And that depends on the axial confinement. So that's one small tunability we have on the scattering length. However, this won't significantly change the results. One nice thing about the BKT transition is that it is universal. It's predicted that the critical exponent at the transition is 0.25. It has a universal value. The only difficulty that might come from a different interaction strength is that to be in the quasi-2D regime, our temperature, our KBT, has to be less than the harmonic oscillator level spacing along the Z direction, as well as the chemical potential. And of course, if I change the scattering length, the chemical potential will also change. I hope I was able to answer all the questions. Is there any other questions that I can answer?
Hi, Abel. Thank you very much. Very clear explanations. Okay, let's see here. You have any other questions in the public? If you have, please come on here in front. No other? Okay, I tried to update the page too. I think is not have any other question here also in the chat. I try to update the page. But okay, Abel, very interesting work. Thank you very much. Now we will call your next speaker. You'll be the Abik Kumar Saha. I think I will project his
Yes.
poster here. Hello, Abik. How are you?
Yes.
Morning.
Am I
No,
audible
not
to
afternoon
everyone?
already. Sorry.
Okay.
Could you
Great.
please introduce yourself briefly, and
Yes.
then you go
So,
to the questions.
okay. So my name is Avik Kumar Saha. I am a final year PhD student at Indian Association for the Cultivation of Science, Kolkata, India. And this work is done with the collaboration of one of my professor, Roman Dupsi. And so the main aim and mean the of this project is to finding a phase diagram of the post-Josephson junction. So if anyone know the post-Josephson junction physics, so there is a transition from Josephson oscillation to MQST, and also there are some transition from Josephson oscillation to dissipative regime. So here in this work, we want to categorize, or we want to put all those transition, all those regime into one picture. That is the phase diagram picture, where in phase diagram picture we mainly uh, uh, see various regimes like Josephson oscillation, self-trapping, and shockwave and overdamped oscillation, and we mainly solve the Prosperovsky equation using imaginary time method, and we describe all those regime, and this kind of dash line the approximate analytical results, and the density fluctuation are shown in the third para of my poster, and with the Feslen portrait, and in the final para we have verified the phase diagram with the when variable is time dependent, I mean point to a time. So then we have different kind of phenomena, which is self-trapping resonance. So the question here in Sao Paulo, one of our research areas is quantum turbulence. Do you think this protocol could be used to achieve turbulence? Okay, so the two situations we have used, one with the fixed tunable, one with the fixed barrier, which is tunable, and another with time dependent barrier. But as far as I know, in kind of reaching the quantum turbulence, we have to modulate the barrier. So one can reach the turbulence state here if one can modulate the time barrier, time dependent barrier vertically, or one can move the barrier vertically, axially to this, I mean the oscillating back and forth to the double L potential. But particularly this case, quantum turbulence is not possible. But if we modulate the barrier, whether it is vertical or with the axial, I think one can achieve the turbulence state. But still, this the whole work is done in 1D. I don't know there is any term related to 1D turbulence. So maybe if there are terms referred as 1D turbulence, then we can achieve those things with this type of configuration. Any question?
Okay, Abik, sorry. Is there another questions? Oh, please, Alex, come here. You have one of the participants here to make a question for you, Abik. Just a minute.
Okay.
So, hello, thanks for the great
Hi.
poster. And,
Thank you.
I see that you have a quench protocol, but in some cases, I use it to beyond mean field calculations, and we usually produce some fragmentation when we do these quench protocols. Do you think, is it the case in your work, or the fragmentation of the condensate state is negligible?
Yes, I think because in the second case, when the quench is considered, we initially consider too high barrier height so that the both two bees either decouple from each other. So this is actually, and then we kind of lower the barrier. I mean, the tunable barrier is lowered such that the kind of BEC is initially decoupled and then they coupled via this barrier. So I think this configuration is very much useful. But regarding the fragmentation of BEC, I am not sure actually, because I don't know.
All right, thank you.
Thank you, Alex.
Okay.
Is there another question? No question? Let me see a bit if you have someone here in the chat. You have to update the page. Just a minute. I think it's not. Then thank you again, Vic, for your participation.
Thank you.
Thank you. I will call the next participant. It will be Alejandra Del Rio. And he'll talk about collective and nonlinear excitations in an interacting superfluid confining NatPaz 2D trap. Now, let's wait for Alexandra.
Yes,
Are you
hi,
listening?
hi everyone. Yes, yes, well, actually, I'm doing my PhD in a lithium experiment in Mexico, and well, the work that I present is about a variational study of collective and nonlinear excitations in the ultra cold cloud, and well, I am going to answer the questions, the 2 questions that I have, and yes, well.
Oh, sorry, Alejandra. I think you stopped to listen you.
Oh, I was unmuted. I'm sorry.
Can you start
Okay.
again, Alessandra? Sorry, just for the questions.
Yes. Okay. Well, I will answer the questions. And I was saying that the Gross-Pitayevsky equation was solved numerically, but it was not made by me, but by another student. His name is Diego, and his poster is in page 2, where you can see the simulations of this parametric modulation of the trap. Yes, since we solved this using the variational method, we noticed that we limit the physics we observe are limited by the ansatz we choose. So in our case, with a Gaussian ansatz, we are only able to reproduce the collective modes and not the Faraday waves, since for seeing the Faraday waves, we should consider a variational parameter with a spatial dependence. And the other question is how we can found the resonance values, and the resonance values can be found if we diagonalize the matrix of the couple equations we found. And well, also we knew the values because we did this experimentally, and so we know at what values of frequency we can observe this phenomena. Yeah, that's all.
Okay, thank you, Alejandra. Is there another questions? No other? Okay, I have a question, Alejandra. I think you tell about this spatial modulation. I think in the past we try a work here in our group in São Carlos, where we try to simulate collective modes coupling. When you consider in your variational parameter a scattering length that it changes with the position in the trap, like you have a flashback resonance simulating a flashback resonance in your system. And it was a paper from 2012. And maybe I will give you the reference because I think it's very interesting. It looks like your work here. It's very interesting.
Okay, thank you.
Okay, thank you, Alejandra. Our next speaker will be is almost there. Alexandre Andrade Cavalcante de Almeida. He will talk about forward degenerate for wave mixing line shapes in cold rubidium atoms using a single CW laser. Okay, let me see here.
Hey everyone, can you guys hear me?
Yes, you can hear you. Just a minute.
Okay,
You
great.
found your poster? Okay, please go on, Alexander.
Okay, so, well, first of all, thank you, the organizers and everyone on site and online for the presence. My name is Alexandre. I am a PhD student from in the Federal University of Pernambuco in Recife, Brazil. From the Brazilians, they don't know where Recife is, but the non-Brazilians, Recife is the northeast of Brazil, right there on the tip. And this is a work with four-way mixing we've been doing for a few years now. We've been exploring this type of forward degenerate four-way mixing and trying to look for spatial and frequency correlations between these signals. So what we do is quite simple. We have, in this work, a sample of cold atoms, but we did the same thing with a sample of hot vapor, of rubidium vapor. And we use a single laser to generate two input beams and then induce two similar four-way mixing processes. So you have two transmission signals and two four-way mixing signals. Yeah, it's quite over that nice figure. So the main idea, and that already answers the first question in the chat, was to look for correlations between these signals. We wanted to generate the two four-way mixing signals and look for time correlations between them. We expected these correlations to be classical. We do know that the probe beam and the generated field in a four-way mixing signal, they are untangled. But the question we wanted to answer was, is there some correlation between the two four-way mixing signals, these two four-way mixing signals? So this was the motivation behind this work. But as we did the first experiment with using the cold atoms, we saw a spectral feature that at first was unexpected. We saw that the spectrum had a deep right on resonance. So you should expect that the signal would be just a peak, but we got a double peak structure with a valley on middle. And the idea of the poster is to explain this feature and why is there a valley right in the middle of the signal. But the motivation behind it was to study correlations. Since we got a weird spectrum, we wanted to first explain the spectrum and then move on to the correlation. And well, just to tell you guys what is the reason behind this dip, you see there in the figure of the experiment and the theory, this is a spectrum changing intensity. What happens is you get a coherent population trapping. Since you have both input fields changing the frequency simultaneously, they induce a coherent superposition of the populations, and this cancels the mixing process right on resonance. It is a weird coherent population trapping, I must say so, because it's not a thin spectral line. It's quite a wide valley, but that's due to the changing frequency of the two fields. And then the second question of Vanderlei was, he asked that thing about the temperature. Yeah, thank you. What is the role of the temperature on the visibility? So in the experiment, we did not change the temperature of the cloud smoothly, but I did the experiment also on atomic vapor, so I can tell you what happens if you change the temperature too much. You get a lot of influence of the Doppler broadening, so you won't be seeing this CPT effect that easily, because in a vapor you would have the full wave mixing happening in all of the 3 allowed hyperfine transitions, and it would broaden the entire signal. We believe that maybe if you are very, very careful, you can see it, but we are still validating the data to be sure that it is in fact CPT in the vapor. But I think Professor van der Leyen wanted to know if I went below this temperature because he works with BEC. Well, we are using a magneto-opto trap. We have a temperature, I think, of 300 microkelvin, so it's quite over the TC. And well, for the CPT, I don't really know what would happen for the full wave mixing signal, but I think that for our main goal that was studying the correlations, we would get interesting results using a BEC, because you would have interaction between the atoms. So that probably would change the correlations between these 2 signals. Maybe it wouldn't be so classical anymore. Is there any other questions?
Is that another question? Van der Leyen, want to make one more? No, satisfied with your answer. Thank you very much, Alexander.
Okay, thank you.
Then we go ahead with our next speaker, will be Ana Karen Cuevo Montiel. She will talk about variational approximation for the dynamics of a quantum gas in potential with curvature. Let me show her poster.
Hi.
Hello, Anna?
Hello.
I can hear you, yes, but I can see you. I think your camera is turned on.
Okay.
But you can listen you very well.
Yeah. Well, my name is Ana Karen Cuervo, and the work that I will present is entitled Variational Approximation of the Dynamics of a Quantum Gas in Potential with Curvature. In this work, the variational method applied to quantum gas system and curved surface is studied. We're using the Gross-Pitayevsky equation. A Lagrangian approach is carried out using the thin layer quantization described by Da Costa to propose a Lagrangian density that allows you to obtain the equation of motion of the system in such a way that a variational treatment can be applied to the density. Thus managing to deal with the problem in an excessive way in order to obtain detailed information about the system. For the question by Emmanuel, which kind which kind of dynamics and or excitation are you interested in observing? So for now, we are interested in the adequate treatment for a good interpretation of the solution to the equation of motion of the system. As in this work, we separate the part of the movement respect to the surface that is on a 2D plane that curves. The interpretation, the dynamics of the equation becomes unintuitive, but since they are a function of the parameters of the surface metric, it is expected that their movement will have a correspondence with node dynamics, where equivalent symmetries are present. In addition, a system was previously studied where a toroidal type potential composed of harmonic potential and a Gaussian beam is proposed. In this way, we can make useful comparisons of the dynamics of the system. That's it. I don't know, another question?
Thank you, Anna. Is there another questions? Okay, I think it's not. Let me see if in the chat have another one. I just updated here the page. Okay. Oh, thank you very much, Anna.
That's it. Thanks.
Okay. Now we will continue with your program. Just a few minutes, then we will start with Professor Hulet.
So, good morning again. Welcome back. And let's please continue the lecture of Professor Randall Hulet, speaking about the physics of one-dimensional systems. Please, Dr. Hulet, go on.
Thanks, Gustavo. Good morning, everybody. I hope it's not as early there as it is here. I guess it's not. So last time we finished yesterday with a discussion of quantum magnetism with ultra-cold fermions. And this was an example of quantum simulation where one could use the versatility of atoms in optical lattices to realize a Hubbard model. And what I want to talk about today is a more recent experiment that is also in the same class of quantum simulation. But in this case, it's the physics of fermions in one dimension. And as you'll see, one-dimensional Fermi gas is a paradigm of strongly coupled or strongly interacting gases that has some really amazing and startling effects. And what I want to talk about specifically is an experiment that we have just concluded. We have submitted the paper recently and it's on the archive. And this is an experiment to observe spin charge separation in a one-dimensional Fermi gas. The people in blue are the experimentalists at Rice who have been involved in this experiment. Particularly like to acknowledge Ruin Senaratny and Daniel Cavazos, postdoc and a research scientist now, and graduate student respectively. And we've had a very nice collaboration with the theory group with Han Pu at Rice, Shi-Wen Guan and his group in Wuhan, and also prior to that with Terry Giamarchi and his postdoc Fiwatis Greason in Geneva. So by the way, in case you're wondering, this is a picture of the inner quad at Rice. So this is the first building on campus. The second building was a physics building, and that's this one. It's no longer a physics building, it's too old, but it's a beautiful old structure and has some great lecture halls in it. It's a real classic academic building. I love that building. But unfortunately, our department, well, maybe fortunately, is now in a very modern laboratory building that's glass and brick and very sleek, very different than the character of these older buildings. All right, so it turns out that excitations in one dimension are quite different than what we are familiar with generally in 3D as physicists. In non-equilibrium situations, one has excitations and transport of particles. And in 3D, if you're talking about electrons and solids, and let's discuss first the electron model, and then we'll go and talk about ultra-cold atoms. But in 3D, electrons are able to move around other electrons. So if there's an excitation, if one electron is moving, it can move around other atoms or other electrons and not be perturbed by them. In which case, the quasi-particle excitations are really single particle-like. So the excitations are fermionic and act like they were a Fermi particle, another electron, with a mass which is renormalized due to the interactions with all the particles around it. This forms the basis of the Landau Fermi liquid theory, and that theory is quite well tested and works wonderfully well for most electronic materials, except for the ones that are strongly correlated. And in 1D, the strong correlations become particularly pronounced. So in 1D, unlike 3D, if you have an electron that is moving, it has only one way to go, or it has two ways to go. It can go to the right or to the left. And in this picture, if this electron goes to the right, it inevitably will come upon another electron, and they can't avoid their neighbors. And so the the excitations are collective rather than quasi-particle-like. They turn out to be sound waves, and they're bosonic in nature. They're not the fermionic electron excitations, they're a bosonic excitation. And the low energy version of this theory, the low energy understanding of this system was given by Tominaga and Ledinger some years ago. Now, the particle hole excitations in 3D in the Landau-Fermi liquid theory can be understood from looking at the Fermi surface, the Fermi sphere. So this circle represents a sphere in 3 dimensions. And you could see that because the Fermi C is full, and typically because we saw last time that in metals, the Fermi temperature or Fermi energy is about 10,000 degrees Kelvin. And so at ordinary temperatures, this Fermi C is completely full, and any kind of excitation has to take place on the surface of the Fermi sphere. And so if you have some momentum transfer Q, it has to be less than 2 kF to stay on the Fermi surface, but it can be anything from between 0 momentum and 2 kF in momentum space. So this is the electron, this is the energy spectrum for the electron, and you can see that there's a continuum of energies that are allowed for momenta transfer that are less than 2 kF. So 2 kF means going from one side of the Fermi sphere in momentum space to the other side. The radius is 2 kF, and the radius is kF, and the diameter is 2 kF. Now in one dimension, it's really very different. And this was given actually by the Yang-Godin model. And the Tominaga-Ledinger liquid is a low energy theory of low energy excitations. The Yang-Godin model is more general. It includes energetic excitations as well as the low energy excitation. Now, as opposed to 3 dimensions, the Fermi surface in 1D is 2 points. So this is minus kF, and this is a momentum of kF, or you could actually call this momentum 0, and this momentum is 2 kF. And so instead of having a Fermi sphere, we have Fermi points. And the excitations can be either, since they have to transpire over the Fermi surface, the Fermi points, all you can do is have a momentum transfer, which is approximately 0, or you could have a momentum transfer, which is 2 kF. And so those are the 2 possibilities, and they're shown here in this energy spectrum. This is energy versus momentum. And you can either have excitations which are near 0 momentum, or excitations that produce 2 kF of momentum. So the low energy excitations that happen at very small q that are given by this circle. This is the dispersion relation, and you can see that the dispersion relation is that for low energies is linear, and a linear dispersion relation is what a sound wave has. So you know that for a photon, that omega equals Cp, or relativistic massive particle, it's the same, has a sound-like excitation. And that's true in one dimension as well, even though the underlying, this is a non-relativistic theory, and the underlying dispersion is quadratic in momentum. For low energies, there's a way of linearizing the excitation spectrum, and this forms the basis of the Tominaga Ledinger liquid theory. So here's a quadratic dispersion. This is energy versus momentum, and this is what you have for a free non-relativistic electron. And you can have again excitations on the Fermi surface, and they can be in one dimension. They can transfer momentum of Q, which is close to zero. That's portrayed by this little this curved line showing an electron being pulled out of the Fermi C, very near the Fermi energy, and being pulled out and being lifted into an empty Fermi C above the Fermi energy. And likewise, you could have, as I showed before, you could have momenta that transfer 2 kF of momentum. And that's given by this line that goes from one Fermi point to the other Fermi point and imparts a net momentum of Q. So excitations are sound-like for small q. We can take the quadratic dispersion and linearize it. You can see for yourself that if Q is small compared to KF, that the dispersion relation is approximately equal to the momentum h bar VF. This is the Fermi velocity. H bar VF times Q, the momentum Q. All right, so when these excitations occur, these low energy excitations occur, there are actually two kinds of excitations in one dimension. One's called a holon, and the other is called a spin-on. And one carries, as you can imagine from the name, one of them has to do with charge excitation or density excitation, and the other has to do with spin excitation, an excitation which carries an excess of spin. So this is a spin-a-half system, and at low temperatures, at very low temperatures, this system will arrange itself with antiferromagnetic correlations. And these are very much like the Hubbard model in that this is the configuration which lowers the energy. This is the ground state configuration of one-dimensional Fermi gas, spin-a-half Fermi gas. So what happens is you start off with everything, let me get my pointer there. So you start off with these alternating spin structure, up, down, up, down, up, down. And there is some kind of an excitation, something imparts some momentum and energy to the system. And that can move one of these electrons away from its equilibrium position. See if I can get my mouse to work a little better. So it can produce a hole by this excitation in the charge or density, and I'll use those interchangeably. So for an electron gas, for an electron which has charge, charge and density are completely equivalent. And for a neutral experiment like a cold atom experiment, there's really no charge to speak of, but nonetheless, we can still talk about charge in the context of density. So charge means interchangeably density. And so this kind of excitation process that we're seeing here produces a hole in the density, and that the minimum of density that occurs where the electron was now appears at some other location. and that density wave can actually propagate down this one-dimensional axis X. Likewise, there can be a spin excitation. So there can be a downspin electron which exchanges with an upspin electron, and during that exchange process, then it produces a spin defect. In fact, two of them. These two spin down electrons, and then these two spin up electrons produce a deficit of spin at this location and an excess of spin at this location. So it looks a lot like this, the density wave, called the charge density wave. But in this case, it's a spin density wave. So these are these are what the excitations look like. These are bosonic operators, and one can calculate the in perturbation theory the effect of interactions. Gamma is the interaction parameter. It's called the Lieb-Liniger parameter, and it depends on a 3D scattering length, and it depends on the 1D density. So, and the charge, what the prediction is that the charge excitation, the charge density wave, will increase in speed with increasing repulsive interactions, whereas the spin excitation will decrease in speed. And so, symmetrically, according to perturbation theory. In reality, a more complete theory will show that these increase and decrease in speeds are not the same. They're not both equal to gamma over pi squared, but they're different. The spin actually reacts a little bit stronger than does the charge, so it actually slows down with a greater amount of interaction than does the charge mode. All right, so then we get two dispersion relations. We get a dispersion of the charge mode and a dispersion of the spin mode, and they're different. One of them is predicted to go more slowly, and the other one's expected to, with increasing interaction, go faster. Now, think about that for a moment, because this is a profound statement. It's saying, here I have some property of the electron, its spin and its charge, and that property of that point particle is now in this collective one-dimensional setting are moving at different speeds. So if the spin of the electron moves at one speed and the charge of the electron moves at another speed, it means that eventually they're no longer in the same place. So the spin and the charge degrees of freedom of the electron have moved apart from one another. And that's just weird. That's just an amazing result. And it's very remarkable and surprising in many ways. So this is called spin charge separation, and it's a hallmark of this Tominaga-Lettinger liquid theory. And it's also an example of fractionalization in strongly correlated systems. All right, so did I go the wrong way or did I go backwards? Here we go. I'm going backwards. Why am I going backwards? I don't know. So there have been experiments to probe this kind of physics. First in the solid state using electrons. People use nanotubes, which incidentally were grown in my colleague's lab at Rice, Rick Smalley, my late colleague. Rick won the Nobel Prize for discovering the C60 molecule. And he also did a lot of early work on carbon nanotubes. And so this group used nanotubes from Rick Smalley and were able to observe power law correlations of the electron spin and charge. And these correlations are also another manifestation of the Tamanaga-Lettinger liquid theory. This group, Amir Yacobi's group at Harvard, it saw the fractionalization of charge and spin using heterojunctions. And this is a plot of the Fermi velocity over the velocity. So this is the inverse of the velocity along this axis. And this is the carrier density. So they don't have Feshbach resonances in semiconductors, but so they can't really control directly the interactions, but they can control the density. And the density also plays a role in the speed of these excitations. So they were able to see the fractionalization of these quantum numbers, the charge and the spin. They're propagating at different speeds. And that's the hallmark of spin charge separation. But they were unable to do quantitative comparisons with theory due to the complexities of the Coulomb potential and the unavoidable disorder and lattice defects that one has in real materials. Okay. So I think that's what I need to say about that. Oh, okay, there was another experiment using angle resolved photo emission spectroscopy in which they were able to see two dispersion relations, the holon, the charge density wave, which is given in blue, and the spin density wave, which is given in red. And you can see that their dispersion relations are different. All right, so there's also been some very nice cold atom work, one by the group in Florence, Leonardo Filani's group, and my colleague who was a graduate student at the time, Guido Pagano, did this experiment in 2014 in which they measured what's called the dynamical structure factor. So the dynamical structure factor gives the density and spin correlations that describe how these low energy excitations occur. So in the experiment, they used ytterbium-173, and there's no Feshbach resonance. So they're able to get the dynamical structure factor for the charge mode, and this width has to do with the inhomogeneous density profile of the atoms in the trap. But they're unable to tune the interactions, and they're also unable to excite a spin mode due to the fact that there's no hyperfine splitting in this atom. But they were able to use the spin multiplicity to show the difference in speeds between essentially an ideal Fermi gas and one which is weakly interacting. So this was a pioneering experiment back in 2014. There's also experiments that have been done in Munich in Emanuel Bloch's group, and their experiments were not really low energy excitations, but rather high energy excitations. They were looking at deconfinement transition, where they take a lattice of a two-dimensional lattice with site resolved atoms and remove one of them. And when you remove one of the atoms, you excite all kinds of high energy excitations, both in the spin sector and in the charge sector. So they were again able to observe fractionalization, but not really compare to linear liquid theory at low energy. There is no low energy excitation. So, so how does this, how can you measure this dynamical structure factor? Well, you can use something called Bragg spectroscopy. So the idea is to use, in these cold atom experiments, is to use a two-dimensional optical lattice that produces a bundle, a two-dimensional array of one-dimensional tubes. So each of these tubes can be made isolated from the others. And so you can study one-dimensional physics that is an average over all of the fillings of each of these tubes. So in our experiment, there is something like 1,000 tubes, and each tube has something like 60 atoms in it. So Bragg spectroscopy works by imparting momentum in an energy resolved way. So the momentum that you transfer, here's the tube in blue. The momentum you can transfer in this process, this is 2 laser beams, one laser beam at momentum K1 and energy omega 1, and another laser beam that comes in at a momentum and frequency of K2 and omega 2. Now, by absorbing one photon and stimulating to emit another photon, you can undergo a Bragg process where the momentum transfer is equal to K1, this momentum, minus K2, this momentum. And so that momentum transfer depends on the angle between these 2 laser beams. And for our experiment, this angle is about 4.5 degrees. And so the momentum transfer is a small fraction of Kf. So we're in the low energy excitation regime. Q is about 0.2 of Kf. And because you can make these laser beams to have some frequency offset from one another, you can make the frequency offset omega 2 minus omega 1 to be anything you want. You just dial in the frequency of an AO modulator, and the typical frequencies are about 10 kilohertz. So the typical frequency omega is about 10 kilohertz. So this is called Bragg spectroscopy. So you have some fixed angle, and as you tune omega, you tune excitation resonances tune those excitations into resonance. And so you can map out this dynamical structure factor. Now turns out that you can, by adjusting the detuning, the overall detuning of these laser beams, you can excite a symmetric mode in which the laser beams are equally detuned to both the upspin and the downspin atoms. So I detune far compared to the splitting between these 2 states. These are 2 hyperfine sublevels of the ground state of lithium. And that frequency splitting is about 100 megahertz. But this detuning can be made to be many gigahertz, in fact, about 10 gigahertz. And so the spin part of the excitation drops out, and one excites only a charge excitation by this detuning scheme on the left. Then on the right, if you tune in between these 2 states, these 2 hyperfine sublevels, you have equal magnitude but opposite sign detuning, you can excite a spin wave. And so the spin wave happens because the light shift of this Bragg pulse is detuned oppositely in sign to the light shift given by the other one. So one of these lasers, the lasers are either blue detuned with respect to one spin state, but they're red detuned with respect to the other. So this is a real powerful fact that you can excite symmetric modes that give you excitations of just the charge or the density wave, or you can excite just spin waves, and you can do that completely independently. So the spin wave can be excited independently of the charge wave. All right, so this is what the Bragg signal looks like. So if you take an image of the, after time of flight, of the atoms that are in this bundle of tubes, you get a column density image that looks like this. And in this image, the tube direction is horizontal, going across the page here. So here's the tube axis, calling it Z here. And now let's turn on the Bragg pulse. So we'll turn on those two laser beams at a small angle. We tune them on for about 300 microseconds. And you can see that there's something going on. These images are not exactly the same, but if you subtract this reference image from this image, you'll find that you have some regions where you've outcoupled atoms, and those are shown in red. You've imparted momentum to them from the Bragg process. And where they came from, the deficit of atoms is shown in blue. And again, the tube axis is horizontal. And the reason why it's bigger perpendicular to the tube, these regions are elongated perpendicular to the tube, is because of confinement in the tube. So the radial confinement is so strong when you release them in time of flight, they mostly expand radially and very little along the tube direction. So the momentum transfer that you see going from the blue to the red regions is due entirely to the Bragg momentum Q. So it turns out in low enough excitation energy of the Bragg lasers, the total momentum transfer is proportional to the dynamic structure factor, the factor that depends on both Q and omega. And that was shown long ago by David Pine. So if we look at these images again, the difference between these two images, then integrate along this direction perpendicular to the tube axis, you can get line density plots. And the red is showing the line density without the Bragg pulse. The green down here, you can barely see the shoulder, is showing the line density with the Bragg pulse. And then this is the difference. And so the difference between those two images, when I integrate perpendicular to the tube axis, gives me this line density, and that's my Bragg signal. That's what I plot in the following slides. All right, so measuring the dynamical structure factor of the spin wave has proven to be difficult. So several years ago, we were able to measure the dynamic structure factor of the charge density wave in this way, using this far detuned laser beam. But now, to measure the spin density wave, this laser detuning from resonance is only half of 80 megahertz, it's only 40 megahertz. So there's a lot of spontaneous emission, and the spontaneous emission causes heating. And so we were unable to actually show the spin charge separation because we could not measure the spin density wave. We could only measure the structure factor for the charge density wave. So we came up with an idea. This is the red transitions shown here are the usual 2S to 2P transitions that people use in lithium. This is at 670 nanometers, the red transition. And what we had done several years ago was to use that 2p excited state as an intermediate state in this 2-photon Bragg process. But what we realized is that there's another state, there's a whole sequence of them. The 3p state turns out to have about a factor of 8 longer lifetime than the 2p state. And so the longer lifetime actually translates into less spontaneous emission. And when we do the Bragg process, we do use the 2p state for the charge density wave, and we use the 3p state for the spin in order to use a state which is a narrower line width, and therefore less spontaneous emission. And this is what we get. So on the left are the dynamic structure factors for the charge wave as a function of interaction. The red ones down here correspond to a free Fermi gas, non-interacting gas. The yellow to 100 Bohr. The kind of reddish brown one is 200 Bohr. The green one is 300, 400, and 500. And as you go up in interaction, if you look very closely, you can see that the peak is moving to higher frequencies. And the frequency corresponds to the speed, because the momentum is fixed. The peak frequency actually corresponds to the peak speed of the gas, and the most likely speed in the gas. And we can also now do it for the spin wave, because we're using this 3p transition, which is narrower. And you can see here that, in fact, the effect is bigger. As I was mentioning earlier in the beginning of the talk, the effect on the spin wave is greater. And here we're going from essentially an ideal Fermi gas to a relatively strongly interacting one. And you can see that the peak in this structure factor has moved. And the solid lines are theory, and there are only two free parameters in this fit. One of them is the temperature that fits, the best fit is 250 nanokelvin, which is quite reasonable, and the overall scale factor for the structure factor. And it turns out that the theory for the spin wave also requires nonlinear corrections. So what we talked about was a linear dispersing sound wave, but there are also nonlinear corrections, mainly due to something called backscattering, which is it's a little bit complicated, but it's a two spin-on process. So again, this is the data with comparison to theory, and the comparison to theory is really quite remarkable, I think. The theory done by Jiwen Guan and his students and postdocs. This is the first time that there's been a quantitative comparison between experiment and theory for the dynamic structure factor of spin and charge modes of a Tamanaga linear liquid. And if you take the peak and plot that peak, omega p, which corresponds to a peak velocity, as a function of interaction strength, this is where the Feshbach resonance comes into play, because we can tune the S-wave scattering length to different values. You can get the speed of the spin wave in blue in comparison with theory, and the speed of the charge wave given in red. So the charge wave actually speeds up with increasing interaction, but the spin wave slows down, and they very clearly have different speeds. So this is the spin charge separation. All right, so as I mentioned, we have evidence for nonlinear effects. And the evidence is most pronounced in the spin wave. So if you look at those these different images, the Bragg signal minus the reference signal, you see it for a non-interacting gas, for charge and spin, they basically look the same as they should. The velocity of the charge and the spin wave should be exactly the same for a free Fermi gas. But if you go up to strong interactions, the spin dispersion appears to be nonlinear. It's no longer very well-defined momentum, but rather the momentum is spread out. And this is an effect of the nonlinear part of the excitation, nonlinear part of the dispersion relation, and had never been seen before in a quantitative way. So this is the spin mode, the charge mode, the width of these peaks in position space. So the charge mode essentially is still linearly dispersing. There's a small amount of nonlinearity, but for the spin mode, it's really quite pronounced. There's quite a bit of nonlinearity, and the width of this of the outcoupled atoms in the spin mode, it really depends very strongly on the interaction strength. So it turns out that this is an indicator that backscattering and other nonlinear effects have to be taken into account for the spin mode. So these nonlinearities that can cause this dispersion are things like band curvature. And if you recall back early on, I showed the dispersion relation. Let me show it again because I think it's worth seeing. Where did you go? Oh, here. So you can see that for low energy excitations, that this is quite linear, this dispersion. But as you go up in momentum, you get nonlinearities. This curve starts to turn over. And that's the effect of band curvature, it's called. Let me go back to where I was, which is here. And there are other sources of nonlinear effects as well, spin charge coupling and backscattering. And backscattering is the collision of these two different spins, and one from each Fermi point, and it's exclusive to the spin sector. And so the spin wave shows this backscattering effect, and in fact, it's dominant. In order to compare successfully with theory, you have to take into account backscattering. And that was a real tour de force by the theorists in our collaboration to be able to do that. All right, so let me just finish up by mentioning another experiment that we've been doing, which is to look at spinless 1D fermions near a P-wave Feshbach resonance. And the motivation for this is that you could realize the Kitaev model of Majorana fermions if you have a topological superconductor, which a P-wave superfluid is, or a P-wave superconductor is. So there are, as far as we know, no P-wave superconductors have been conclusively discovered, which is pretty surprising. There are some candidates, but what we would like to do is to engineer a P-wave superfluid by using a Feshbach resonance to make to induce P-wave pairing between identical fermions. And so we tried to do that in one dimension. We did do that in one dimension. And what we found was that the P-wave pairs have a very short lifetime near the Feshbach resonance due to inelastic collisions. So we need to find another way because this motivation is quite strong. This is really important. And we think that, there are perhaps ways of finding better Feshbach resonances that are broader that would have less loss. And I mentioned the experiment that we did several years ago on the dynamic structure factor of charge waves. And this is the work that I talked about mainly today. The spin charge separation is on the archive. All right, so let me acknowledge the people who did this work. The primary people were Ruin Senaratne and Danielle Cavazos, and now graduated Yating Chang, and also Ernie Yang, who's had graduated when this picture was taken. And also our theory collaborators, Jiwen Guan, theory collaborators sit above us in some higher plane, I guess. This is Jiwen, he's from Wuhan, and Han Pu is in our department, and Thierry Giamarchi and his postdoc, Piwatis Grisons. So that is it. I think that's all I need to say. So thank you very much for listening.
Thank you. So we're open for questions. Do we have questions, comments?
Particularly questions from the students would be quite welcome.
Sure. No question? Okay, then. I guess that's it, Randall. I'm still learning a little bit. I need to read a bit more to ask any questions about your recent works. So I thank you once again, and let's finish the session. Thank you.
Yeah, my pleasure. Thank you. Right.
Hi, everybody. Good morning. I'm here just to remember about the virtual presentation from the lab.
Okay, everybody, we're ready to restart. Carlos is online, so I think he will appear in the screen soon, but I start. So Carlos got his PhD from Stanford University with Professor Doniak. Then he was a postdoctoral fellow in Illinois, and then at the Argonne National Laboratory working with Abrikosov himself. And he is currently a professor at Georgia Institute of Technology in Atlanta. He has been working for very long in superconductivity and superfluidity. And today and tomorrow afternoon, he's speaking about supersolids in ultra cold atoms and dipolar molecules. Carlos, welcome. And yeah, feel free to start.
Okay, thank you very much. I hope everyone is having a very good time in the school. I apologize for not going over. We took the cautious approach to stay and hope everything is okay with the Omicron wave and so on. So I would like to talk about in this series of lectures on a topic which is currently very popular, or came back, I think, which is the topic of supersolids, and with direct application to ultra-cold atoms and dipolar molecules. I will discuss this topic in 3 lectures, and the first of which is today, which I will talk about dipolar boson supersolids in the continuum, meaning on a trap or a box potential. And then talk about the emergence of dipolar boson supersolids in optical lattices, in which you create an artificial lattice with light, load with atoms, and see if those systems behave according to what a supersolid should behave. And then in the last lecture, tomorrow, the last 2, I will talk about the existence of supersolids in spin orbit coupled Bose systems. So today we'll cover only the first part, and I will start then on that. So the outline of lecture number 1 will be as follows. I'll have an introduction to define what would be a supersolid for us, where would they exist in principle. Then since I'll be focused on dipolar systems, I'll review a little bit about what dipolar systems are, or what are those that are available around. Talk about quantum phases of dipolar systems in 2 dimensions, and then talk about the emergence of dipolar supersolids and a melted version of the supersolid, which we call an excitic superfluid, and conclude. So one of the things that I typically do when I lecture, I just try to give the conclusions more or less up front so that people can know what the lecture is going to be about, and have at least an initial idea what the story is taking you. I will present the same slides at the end as well, so to remind you what I told you. So I'm going to tell you now what I will discuss. So in words, we will have a working definition of a supersolid as being a system which exhibits both superfluid and crystalline order. So that's going to be what we're going to define to be a supersolid in our systems. And then I will discuss in the lectures that ultra-cold atoms and molecules can have supersolid phases, in particular for systems involving dipolar or spin orbit coupled bosons. So systems that have a dipole moment, electric or magnetic, or that you can introduce an artificial spin orbit coupled system can exhibit these phases. And then today I'll focus on dipolar bosons, and particularly in 2 dimensions, and in the continuum or box potentials. This means without any lattice, just something free space or a box potential or a trap that's as flat as possible. So among the several phases that those systems can have, I will highlight 3, which will be a dipolar superfluid, which you already know exists, which has continuous translational and rotational symmetry. A dipolar supersolid phase, which has discrete translational symmetry and rotational symmetry, but also superfluid properties. And a third phase, which we call dipolar excitic superfluid, which has broken discrete translational symmetry, but preserved discrete rotational symmetry. So those will be the things. And most important one is going to be a supersolid. And basically the idea is that you can have a triangular dipolar supersolid in 2 dimensions if you have dipole-dipole interactions. And those systems would form some superfluid droplets with roughly a flat top in density. And these droplets will be more or less phase coherent. So one way for those of you that know a little bit about superconductivity, you can think about this as a series of disks of superconductors which are phase coherently connected, let's say via Josephson coupling. Here you don't have that, you have a continuous system, but which self-organize due to dipole interactions into some islands, and phase coherence between them established essentially via some kind of tunneling process as well, if you wish. Although they can be continuously connected. They don't have to be physically completely separated. Density doesn't have to go to 0 in between the two. Okay, so in terms of a picture also, these phases, this is a phase diagram, schematic phase, well, it's a calculated phase diagram of the temperature divided by the dipolar energy versus the ratio RD of the dipolar energy and the kinetic energy of the system, in which we plot the temperature. At very high temperature, the system is a dipolar normal fluid. At very low temperatures, when the kinetic energy is much larger than the dipole energy, you have a dipolar superfluid. So it's completely dominated by the kinetic energy. And when the system is dominated by the dipole-dipole interaction fully, you have what we call a dipolar Wigner crystal at low temperatures, DWC. And in between this phase, a dipolar supersolid can emerge as a compromise between the tendency for the dipolar energy to dominate versus the tendency of the kinetic energy to dominate. So this is where these kind of droplets would form. And above that, as you increase the temperature, this phase would melt. So a dipolar supersolid would have, if you look at the Bragg scattering or the static structure factor, you would see for a superfluid some signals centered at Q equals to 0, indicating that you have a condensate at Q equals to 0. When you develop this kind of supersolid order, you also have a structure of the lattice, which you have the 6-fold symmetry associated with the hexagonal structure of the lattice in the structure factor. And in a melted phase, this hexagonal structure is still more or less preserved, but translational symmetry is lost. So this means these points here, these Bragg peaks are not sharp. They are fuzzy at the hexagonal structure. You still have a hexagonal symmetry, and that's called the hexagonal phase. It's a superfluid, but has lost translational discrete symmetry, so it's no longer a solid. Okay, so let me start then by discussing what are supersolids, where do they exist? So where this all came from. So the idea of supersolids arose in the context of helium-4, and you know, it can be traced, the early ideas even to the late 50s and so on. But the very first series, I would say, analysis and calculations were done by these 3 gentlemen here, or these 4 gentlemen here, these 3 papers. Andreev and Lifshitz discussed already the possibility of a supersolidity in the paper in 1969. Then Chester and Leggett in 1970 discussed the possibility of supersolidity. The question actually is better phrased in the way that Leggett put it, which is, can a solid be superfluid? So naturally, helium-4 was the known superfluid at the time, and the only one. Then a few years later, helium-3 was discovered, superfluid in helium-3. solid helium-4 was obviously a natural candidate, especially if you look at the phase diagram, which has this schematic one in terms of pressure versus temperature. You have a wide area of a superfluid phase, wide area of normal phase at normal pressures, but at sufficiently high pressures, the system forms a crystal. Could be a hexagonal closed pact or body-centered closed pact, but it formed nevertheless a crystal. And the question arises, if you have a solid, and this is a phase here in this area that the helium-4 is solid, can you have a structure in which some defects or vacancies or interstitials in this lattice can move around, right? Those vacancies, interstitials will be bosons. They can move around, they can move in a coherent state, and therefore they could be a supersolid. So it's like a doped solid. And for those of you that know high TC, let's imagine that you have an antiferromagnetic insulator, you dope it, and suddenly at low enough temperatures, this thing sort of becomes, these holes correlate with each other and form a superfluid or superconductor. Here would be holes of helium atoms that would correlate and become a supersolid. These defects, these vacancies. So that, of course, in 1970, since that, there was a lot of work trying to find out, but everybody failed until in 2004, there was a work from the group of Moses Chen at Penn State, which claimed to have observed, they were cautious by saying probable, but in the paper, there was a huge discussion that it's most likely it is. Supersolids, and there was a lot of work. And then a following paper, and one in Nature, another in Science, was more incisive observation superflow in solid helium, which is indicating that it's also a superfluid. And then John Rappy, who was the advisor of Moses Chen, also jumped into the problem and found out that, yeah, we did see non-classical rotational moment of inertia. So it's a signal of supersolids. And then the disorder doesn't seem to affect much supersolidity. But a few years later, from 2004 to 2006, Balibara was criticizing that work because there was alternative interpretations, and then conducted some experiments also. And then a few years later, those papers were retracted. So Rappy retracted first by showing that indeed there are other explanations for what they observed, like disorder actually played an important role. And then Moses Chen also published a paper indicating that it was absence of superfluidity. Nevertheless, you can see the number of citations of those works is enormous because it's a big and important problem. Unfortunately, there's no superfluidity in helium-4 up to now. Okay? So that was unfortunately not the case. And so then back in 2009, we tried to ask a different question, which was, there was an initial work on dipolar systems, and we were curious when I was using the JQI in Maryland, if a superfluid can be a solid. And so we wrote this paper, which unfortunately only lives in the archive, in which we discussed several phases of supersolids, of dipolar Bose gases. And among them, two that I'm going to concentrate about, dipolar supersolids and dipolar hexatic superfluids. So dipolar bosons, we would argue, are natural candidates for supersolidity. It's not clear that's going to be survive the test of time, but nevertheless, about a year later, there was a work on supersolids on Rydberg atoms by these authors. And again, the same problem was revisited about 6 years later by these authors on proposing essentially the same thing, supersolids in dipolar bosons. So as you may be aware, there are now 3 groups in Europe which have claimed to observe supersolidity in magnetic dipolar systems. 2 of those are in dysprosium-162, which has roughly 10 Bohr magnetons of magnetic moment. And they're cited here as the group of Giovanni Modugno in Italy, Timon Pfau in Germany, transient supersolid properties in those systems, they say also metastable and transient because the system, the supersolid that they observed, lasts about 30 milliseconds, 20 to 30 milliseconds. And then there was also a paper by the group of Francesca Ferlaino in Austria, where they discuss the existence of long-lived and transient supersolid systems in dysprosium-164, notice it's a different isotope, and erbium-166, in which they then create this structure which they believe to be a supersolid. Now, this is a picture from Ferlaino's group showing, I mean, it's a very busy picture. I just want to focus here on those things slowly. So the structure of the system is such that they have these dysprosium and erbium atoms located in a trap, which is elongated like this. A large magnetic field B along one of the directions is called Z-axis, this one here. Y is the direction along of the elongated direction. And this very large direction, all the dipoles are aligned. And what they see is the position along the Y direction, along this thing, on the next in figure B. And as they change the interaction, the scattering length of the system from 44 to 54, I think, in terms of Bohr units. And what they see is that depending on that, they can have a complete sort of Bose-Einstein condensate system that evolves slowly, towards lower scattering length to a supersolid. And this is a cut, and this is a full phase diagram here of the number of particles versus the scattering length. And this cut is right here. So it shows when the scattering length is large, 54, 55, you have a BEC. When you go into this regime here, you have some kind of supersolid. And here you have an insulating droplet phase. So the droplets are completely decoupled and lose phase coherence. Okay, so this is the idea. So we have BEC, supersolid phase, and a droplet phase, which are insulating, which are completely isolated, like a Wigner crystal kind of thing. So for the case of erbium, the lifetime is about 20 milliseconds. Erbium-166, sorry. For the case of dysprosium-164, it's about 150 milliseconds. So this one here is the candidate which is lived the longest. So of course the question is, would these experiments survive the test of time? Of course, more experiments are needed, but it's important to investigate also this phenomena in dipolar molecules and Rydberg atoms, which are around the corner, and then we can see in various systems if those phases exist. But right now, there's a lot of excitement, so it's a very important question, and experimental achievement has been really amazing. So let me review briefly what dipolar systems are. We can have, of course, dipolar atoms, which are magnetic, and I have several examples here. The two of them, dysprosium and erbium, were those what we discussed. They interact via dipole interactions, so which is nice, and they can control this interaction to some extent by the direction of the electric field or magnetic field. But you also have dipolar molecules, which in principle can be used. And there's a big difference between dipolar molecules, of course. You can create dipolar molecules by combining any one of, let's say, these alkali atoms and creating sort of a rigid rotor for those systems. And this rigid rotor would have, let's say, the two lowest energy states, A0 and U1, associated with the moment of inertia of those molecules. The eigenstates are the spherical harmonics. And we can use the dipolar molecules, in principle, right, from those systems, to analyze at low temperatures the systems. Spherical harmonics have well-defined parity. At low temperatures, we do not mix those things too much, so the dipole moments of these molecules are very small. So we need to apply an electric field in order to create a large dipole moment. So unlike the magnetic atoms, dipolar molecules at low temperatures don't have a dipole moment, a substantial one, very small. You need to apply an electric field to induce that dipole moment, while the magnetic moment is intrinsic, it's associated with the spin. So to induce a dipole moment, you can apply a large electric field, and you can saturate those things to values of order of a debye, fraction of a debye. So why ultra-cold molecules, in addition to atoms, magnetic atoms, is because if you have dipole moments of order of debye, this gives you a dipole-dipole interaction, which is about 10 to the 4th times stronger than what the Bohr magnetons will give. So if you've seen those things like this, it's pretty interesting, because you can have from 100 to 1,000 to 10,000 more strong dipole interactions. So therefore, there's more room to find the supersolids in those systems as well. And of course, the dipolar molecules, you can also adjust several things. But unfortunately, those dipolar molecules are not yet brought to quantum degeneracy. So there are no experiments on that front, but they're getting close. So, and the other problem is that you can try to do that with Rydberg atoms, and there's some progress on that as well. So the question is then, if you include these 3 groups, magnetic atoms, dipolar molecules, or even Rydberg atoms, what are the quantum phases that can have in 2 dimensions? So that's what the discussion here that I would like to go about, is that there's several phases, and I'm going to cover them all, but I'll focus then on the dipolar supersolids and dipolar hexatic superfluids, which should be present in those systems. And as we have seen, the dipolar supersolid has been claimed to be seen already. And I suspect they also have seen the hexatic superfluids, but they don't know yet. So let me pick up the example of a dipolar molecule first. We can also always do a multipolar expansion and replace that by magnetic moment. But let me imagine that I have dipolar molecules which are in the presence of an external field, or magnetic moments. That doesn't matter so much, except the interaction will change a little bit. And they interact with each other. So if all these dipoles are aligned to each other, they will definitely, to dipole interactions, repel. Right? You can just do the dipole expansion of this, and you can see that. So the dipole moment is going to be all aligned with the direction of the field. And if you do that, the dipolar regime for this type of Coulomb-like interaction would occur when this distance between the molecules, I mean, this is the size of the molecule, or R, right, that I define here, is much smaller than the interparticle spacing. When that's the case, then we can expand that, and you get the pure repulsive dipole-dipole interactions. But in the Hamiltonian that we're going to be looking at, which is a continuum Hamiltonian, or in a trap, box trap, it has a kinetic energy, has a contact interaction, which is associated with the scattering length of the system, and the dipole interaction coming from here, from the dipole expansion. So you can, of course, write this interaction down in terms, do the dipole expansion explicitly, and then the Hamiltonian can be simplified and written with the kinetic energy, the dipole interaction, which now is purely repulsive because all the dipoles are aligned, and a contact interaction, U, which is controlled by the scattering length. So the relevant parameters, of course, in this problem are the ratios of these energies. So the kinetic energy can be identified with A, let's say A squared being the typical interparticle, spacing. So the typical kinetic energy of the system is going to be proportional to the density. Rho is 1/A squared, roughly. The dipolar energy would be then associated with D squared, the dipole moment divided by the typical separation, A cubed. So the dipolar energy scales as rho to the 3/2. And the contact interaction, EU, which is going to be U, which is this, has dimensions of energy times area, divided by the area, is proportional to rho. So you can see that if we just look at the ratio between the dipolar energy to the kinetic energy, and fix, let's say, the ratio between the contact interaction and the kinetic energy, this ratio of the dipole energy to the kinetic energy scales as the dipole squared times the density to the power 1/2, while the ratio between the contact interaction, the kinetic energy, is independent of the density and independent, of course, of the dipole. So typically, in the early days, people analyze a dipolar superfluid would occur when the kinetic energy dominates, that is, ED is much less than the kinetic energy. And then a crystal, or a Wigner crystal, would occur when the dipolar energy dominates over the kinetic energy. And so if you indeed take the limit in which the kinetic energy dominates, you expect a superfluid. So you can start from this Hamiltonian, and you can have BKT physics that arises. That is in Skosel-Stallers physics in 2 dimensions. So you have a Bose-Einstein condensate, which has superfluid properties. When this ratio is small, you have then a dipolar superfluid. It's completely kinetically dominated. When this ratio is large, the ratio between the dipolar energy to the kinetic energy is very large, then everything is dominated by dipole interaction, and so you expect a crystal, or a Wigner crystal, to form. So just to remind you that this situation is different, RD is large when the density is large. Right? So for the dipole interactions, the fact that the ratio of this energy is proportional to rho to the 1/2 tells you the larger the densities are, the more likely you're going to have a Wigner crystal. This is, of course, very different from the Coulomb case for those of you who are familiar, because the Coulomb energy, Coulomb constant divided by a length, scales as rho to the 1/2, not rho to the 3/2. So this means that the ratio between the Coulomb energy and the kinetic energy is not proportional to rho to the 1/2, but is inversely proportional to rho to the 1/2. So this means that the Wigner crystal arises at very low densities for the Coulomb case, while this Wigner crystal arises at higher densities for the dipolar case. I'm just bringing that piece of physics for those of you who may know about Coulomb Wigner crystals. So then again, in the Coulomb case, you have BKT, now in high densities, and Wigner crystals at low densities. And so summarizing, it's very different from the Coulomb case. That's all the point that I want to make. So when you look at the transition from that to a Wigner crystal, you ask yourself, well, imagine that I have now this set of dipoles, and which are separated by a certain distance A. How can I try to see where in this phase diagram I'm going to have this Wigner crystal form? So you can construct then a lattice of crystals, which on every side of this lattice, you have one dipole moment, and calculate what the energy of that system was going to be for various values of the ratio between the dipolar energy and the kinetic energy. So as the ratio of the dipolar energy to the kinetic energy gets larger and larger, at some point, the system is going to have lower energy. This is the energy of the ground state. 1/alpha here is essentially the parameter that tells you what the size of the wave function of the Wigner crystal in comparison to the distance between the particles in this Wigner crystal. So this is a variational parameter. As a function of that parameter, as it grows, as you vary it, if there's a minimum, but as RD grows, that minimum falls below what the superfluid ground state energy is. So in that case, you have, and that was first proposed by these authors in 2007, that at very low RD, you have a superfluid. It's completely dominated by the kinetic energy. At high RD, you have a Wigner crystal, which is completely dominated by the dipolar interaction, and they predicted that there was a phase transition between those two. So the question that actually inspired by that paper, we ask ourselves, well, is there a compromise between the superfluid and the Wigner crystal phase that could occur in between? So we investigated that problem, but first we investigated what happens to this dipolar Wigner crystal. So we found out that those authors missed the melting transition between the Wigner crystal and what I call dipolar hexatic fluid, a fluid phase which has lost translational symmetry but has rotational symmetry. And that has to do with the fact of this two-stage melting associated with the Koster-Stowles-Halpern-Nelson-Young transition, in which you compute the elastic energy of the system and express that in terms of the strain tensor with those two Lamé coefficients, those coefficients of the associated with the elastic energy. You just pick up the structure, you distort it, and compute the elastic energy, how much energy gain there is when you distort that lattice. And since it's dipolar, it depends on the dipole moment, but it can melt in two stages. And that melt in two stages occurs via the Halpern-Nelson-Young mechanism of creation of dislocation. So the idea is that if you have a Wigner crystal, perfectly hexagonal structure, by creating these defects, you're going to separate regions of hexagonal order, which are rotated with respect to each other. So you break translational invariance, but locally, you still have over large domains triangular or hexagonal order. That's called a hexatic phase. So this critical temperature, you can derive the energy of the system in terms of a phase or bond angle, is also related, it's essentially the same kind of mechanism as the BKT transition. And you can find a critical temperature associated with this bond angle phase, which is related to the BKT, which has an expression like this, and find out what the critical temperature of the system is. So as you raise the temperature, the Wigner crystal melts, but it melts first only by losing translation invariance. And then there's a second melting transition when the system loses the rotation invariance. So the dipolar normal fluid has no translation. It has only continuous and rotational and continuous translation rotation invariance, not discrete. So the superfluid, if you look at the Bragg peaks, if you look at the structural factor, you get a peak at the center at KQ equals to 0. If you look at the Bragg peaks for the Wigner crystal, you have the 6 sharp Bragg peaks indicating they have a lattice structure. And if you look at the hexatic phase, you're going to have this blurred hexagonal symmetry. So indicating that you have local hexagonal symmetry, but you lost translation invariance because those peaks are no longer sharp. So then, of course, we led to the question, is there any additional phases that we can have? And we were motivated in part of that by some work that we knew in the context of excitons, and which was a work by Kielsen and Spivak, in which they looked classical dipoles, exciton dipoles on layered systems, and they asked themselves, is there a possibility that you can have regions in which these exciton dipoles would form kind of droplets? So they were not, they were looking at classically, and they were not interested in supersolids, but nevertheless, there's these classical droplets that would arise for classical dipoles. So the question was, can you have a quantum version of that, quantum droplets, in which you have these droplets will be then superfluid. So you have regions with many dipoles, not only with only one, as it is in the Wigner crystal. And these regions will have then a density profile, which is roughly flat, over a certain length scale, which we call S. So it's S here has slightly different meaning, is the meaning of the spread in density, where you have many, many, many dipoles. In the Wigner crystal case, you have only one dipole per site. In here, you're going to have a disk with many, many, many dipoles. So it's a way of compromising between the superfluid and the Wigner crystal. So we look at this problem, and that led to the emergence of dipolar supersolids and hexatic superfluids, or we call melted supersolids. So the idea then here is that we would like to look at this problem as saying, well, if there's a compromise between the dipolar energy and the kinetic energy in such a way that you form the superfluid droplets, they need to be phase coherent in order to be superfluid, so that bosons that sitting here can move around from droplet to droplet, right? So some path, I can even draw a little path. So, in order for them to do this, they will need to be phase coherent. So we can imagine like motion of those objects going from place to place in a coherent way. So the droplets, they have to be phase coherent. So we can look at the problem again from the variational point of view. We can create some droplets which have a structure like this, sort of a flat top, and we use a variational form which is going to be a hyperbolic tangent. If you recognize that, this is sort of the dual of what you would see for an order parameter for a superfluid, in which goes to the order parameter goes to 0 at some places, and here is the dual. You have droplets of superfluid, and everywhere else the things is superfluid regions are severely diminished. And using this variational wave function, which gives you a profile in a lattice where Ri is the position of each lattice site, which is hexagonal, these islands would have to have some phase coherence built in. And the question is this kind of solution stable anywhere? So why this would be interesting? Because of course it would be interesting because if you had a dipolar supersolid, you could also have a phase in which this dipolar superfluid could melt, in which the system preserves hexagonal symmetry, and it's pretty much superfluid here in this domain, and pretty much superfluid in this other domain, but these two domains are no longer phase coherent. So not well connected. I mean, because they can still be phase coherent, I should say that. It's no longer well connected because you lost the translation invariance. This domain here is rotated with respect to the other one. But locally, you still have superfluidity and hexagonal symmetry. So that leads also to some melting possibility for this phase, for the supersolid phase. And again, the mechanism is similar. It's the Halperin-Nelson-Young mechanism, in which you create this melting, and you create this kind of defects. But now those defects are defects of the domains of the superfluid droplets, not of individual atoms. And so this means that if you analyze the full phase diagram of the system, instead of having just a dipolar superfluid and a dipolar Wigner crystal at very low temperatures, you also have a dipolar supersolid as a way of compromising between the kinetic energy and the dipolar energy, the kinetic energy. So you create some non-uniform solution in the system, which has both superfluid properties and crystalline properties. And as you increase the temperature from low to high, this supersolid can melt the same way as the Wigner crystal could melt. And in a supersolid, you're going to have the structure factor at Q equals to 0 has a peak, indicating that the system has superfluid properties, and has very sharp or sharp enough, because of some broadening of the crystal of the disk where the superfluid is. You have some very sharp peaks with hexagonal symmetry. And then as you increase the temperature in this region, then you still have the peak at the center, indicating that you have superfluidity. But now the lattice structure gets getting fuzzy because you lost translational symmetry, and you get this excitic phase, even though you still have hexagonal symmetry in the system. So this idea is that the system now for dipolars can have not only a dipolar superfluid phase, which is a compromise between dipolar superfluid and the dipolar Wigner crystal, but also a melted supersolid phase. So the question is, in these experiments, are we seeing something like this, or are we seeing something like that? This is something that I bring up, and hopefully people will try to see if the temperatures are low enough to see really a supersolid, or to see something which is melted. Now, the thing is, of course, the experiments so far, they don't really have not been done yet on a two-dimensional structure, right? The traps are very oblong, so they have seen basically a one-dimensional and getting towards a two-dimensional Wigner crystal. So you have something similar in the one-dimensional case, of course, but in which case you're going to have not 6 peaks, but you're going to have 2 peaks only. So it's going to be equivalent to a dipolar supersolid with a center peak and 2 peaks on the right and on the left. And this melted one will be a superfluid at the center contribution and 2 fuzzy peaks on the right and on the left. But the Bragg experiments have not been done yet, so we don't know if they are at low enough temperatures or not. But definitely they see some signatures of this lattice structure being formed. Okay, so then that brings me to the point that I would like to make, bring to the conclusions, which is, what have we tried to say today? Was to discuss the idea that supersolidity is not going to be present so far in helium-4, but the working definition for a supersolid will be a system that exhibits both superfluid and crystalline order simultaneously. So since the helium-4 case is no longer in the game, new experiments in ultra-cold atoms using magnetic dipole moments have shown that systems can be supersolid, at least so far as they can tell. More experiments are needed to measure different things to corroborate with the interpretation. But this kind of supersolids should not only be present there, they should also exist in dipolar molecules, Rydberg atoms, and spin-orbit coupled systems, which I will talk about next time. What I did today was to talk about the case in which you have dipole bosons in 2 dimensions, which is different from the configuration which experimentally is achieved right now, in which you have a trap, which is essentially where this Wigner crystal or this supersolid is essentially one-dimensional. It's a very long trap, not a flat 2-dimensional trap as I discussed today. But of course, this one is also very interesting. So we're hoping that people that can do box potentials can also trap dipolar molecules to study these phases in 2 dimensions. But the 3 important phases that I outlined in connection to superfluidity and supersolidity were that you have a dipolar superfluid when the kinetic energy dominates, which has continuous and translational rotational symmetry. And you have a dipolar supersolid phase where there's a competition between the kinetic and the dipolar energy, which has discrete translational symmetry and discrete rotational symmetry, as well as superfluid properties. And the dipolar hexatic superfluid, which is a melted supersolid, which has broken translational symmetry. You have these defects that form and break the translational symmetry of the system, but you still have preserved rotational symmetry. So in terms of a picture, the important phase or the new interesting phase will be the emergence of these droplets, which are phase coherent, and they exhibit supersolid properties. The superfluid, the bosons can migrate from site to site and can move around, and while still preserving this lattice structure. So I will just summarize again here that to see those kinds of features, the best thing to do is to measure the structure factor. The supersolid would have a peak at the center and 6 peaks at finite Q, and the hexatic superfluid will have a peak at the center indicating superfluidity and a fuzzy 6 peaks in the outskirts. So I end up here. Thank you for your attention. And the next lecture will be about dipolar boson solids, supersolids in optical lattices. If you have any questions, I'll be able to answer them. Thank you.
Thank you. Thank you, Carlos. Questions? I haven't seen any questions also from the YouTube. I have a question. When I see these lattices or solids, I cannot stop thinking about phonons or excitations of the lattice. Do you think this could be also a way to see the melting of the supersolid from one phase to the other?
Yeah, when you talk when you talk about in 3 dimensions, right? The typical, the Lindemann criterion is the typical one which you use for melting. So the way you want to think about this is that when the fluctuations on the oscillations around equilibrium of the lattice become comparable to the lattice spacing, right? You have the melting transition. That's the case in 3D. Right, so these things start oscillating back and forth, and when these oscillations become comparable to the size, of course, everything gets melted. That's called the Lindemann criterion in 3 dimensions. However, in 2 dimensions, that's not a very good a good way of estimating what the melting transition is. The melting occurs via this mechanism, which is the Halperin-Nelson Young mechanism. So the melting of a 2-dimensional lattice is quite general. I mean, any 2-dimensional lattice would obey this. It's now well established that the melting occurs precisely through the emergence of these elementary dislocations and their proliferation. So it's a bit different in 2D than it is in 3D. But in 3D, yes, using phonons themselves will be very, very much the way to do it. In here, the melting is topological in nature. You create these topological defects, which proliferate and then destroy completely the order, crystalline order of the crystal.
More questions? Yes, Lucas.
Hi, Carlos. Thank you for the wonderful lecture. I imagine there are also fermionic species that have huge magnetic moments, right? So you can also do these things with fermions. Am I correct?
Yeah, let me increase the volume here a little bit. I heard fermionic.
So can you do, are there in nature fermionic species with huge magnetic moments?
Yeah, there are.
So I know the problem is hard as it is with bosons, but have people looked at supersolids in this context of, fermionic, either, 2-component fermions like a BC, BCS type of situation, or even in helium-3?
Yeah, so the supersolids in fermions is, of course, an interesting thing. In helium-3, there's no history of that because of you need to get this solid phase is well established. But in the context of cold atoms, there's still a few groups that are working on this now. But it's a bit, experimentally, it's a bit further into the future. So what is sort of already more or less in the pipeline is the issue of superfluidity in those systems. So there's several lines of work already into that area. The issue of supersolidity, which arises there, of course, is going to be much more complicated experimentally, but theoretically you can play with. Is still largely unexplored. I know only, now, about 2 or 3 groups that are doing. My group, and I know 2 other groups that we are competing on the Fermi front. But it's an interesting topic. The experiments are not that close, but theoretically, it's still wide open.
Thank you.
So, I mean, if it's a good area to go into, I think.
Yeah,
although there are very few groups that I know so far.
Maybe I should
investigating
ask again,
this issue. But it's an important question. So there should be also phases like that. But the first thing you need to do, you need to establish the phase diagram of those systems and see what the superfluid phases are. And that has been done. But the supersolid phases would also appear similarly in the case of what I discussed here, especially if you are in the Bose regime, right? In the BC regime. It's essentially identical in this case. Because when you pair them up, they have to pair up in such a way that dipole moments are still massive, right? They're not canceling each other. So you have to be careful that the pairing has to be to give you a large dipole moment, not a small one.
Okay, do we have a further question, Vanderlei? You raise your hand.
Hey, hi, Carlos. How are you? Thank
Hi.
you for the talk. Why can I, you see, when you saw the picture on the reciprocal space, that's a little fuzzy, can I think about the supersolid as just a super fluid where the interaction are just producing some more localized or some order on the components? Why do I have to think about, why don't I think about just another stage of a superfluid? Why do I have to speak about being a full solid all the time?
Yeah. Well, this is a good question, right? In the sense of the following sense. If you think about, why can you not think about this as let me put it this way, a non-uniform superfluid, right? So the question is that not all non-uniform superfluids have this signature, right? So you can imagine some non-uniform superfluid phases which are which do not have this very well-defined Bragg peaks. So the idea is that in order to have in order to show that the system is a supersolid, it's not enough that you have an order parameter which is non-uniform, right? You can have an order parameter which is not uniform, but let's say if these islands were phase incoherent, there's no phase coherent between those things, then it would not be a superfluid. Just by looking at the density, you would not know, right? So you look then at the static structure factor as a way to see that indeed there is phase coherence established between these different regions of non-uniform superfluidity. And that's what distinguishes a non-uniform superfluid in which these regions may not be necessarily phase coherent. They may not, but if they are phase coherent, then you can call that a supersolid because there are well-defined Bragg peaks associated with the crystalline order. So that's the difference I would make.
Okay, we have a question from YouTube, so from Patricia, about the recent experiments observing supersolids in dysprosium and erbium. Are there still some expected signature of supersolids that have not been observed in those systems?
Yes, many. The supersolid here so far is basically conjectured in the sense of measures of the density profile. So that's why I'm advocating, I think it's important in these experiments, there's no Bragg scattering experiment. So what I would say, in this case, if they do a Bragg scattering experiment, right, and this thing is a supersolid, and this thing is not a supersolid, it's just a droplet crystal. In the Bragg experiment, the droplet crystal, would see a peak at finite Q and peak at another finite Q and nothing at Q equals to 0. The supersolid would see a peak at finite Q because it's one-dimensional, a peak at Q equals to 0, and a peak at finite Q, and this thing has only a peak at 0.
Okay. Thank you, Carlos.
So,
yes.
So using the Bragg scattering, you could answer this question. This would give you 2 peaks. The supersolid supposedly would give you 3 peaks. And the Bose-Einstein condensate give you 1 peak at the center.
Thank you. Do we have further questions? Yes, Gustav.
Thank you. Great talk, Carlos. Thank you. I also want to insist a little bit on the experimental part to ask you if you could point which of the existing dipolar experiments will be the best candidate to search for this exaptic or some other effects, or even to realize this Bragg spectroscopy and get the right signal to finally see.
Yeah, I think, let me go back here to, of course, I'm not an experimentalist. I think that this question is better asked to those guys. But from what I know from the experimental data and the talks that I've seen, at the moment, dysprosium-164 is the best isotope because the lifetime in which these observations can be made is about 150 microseconds. The case of erbium-166 in Fellaini's group, it lasts about 20 milliseconds. And the other 2 experiments, they both use dysprosium-162. But those, the lifetimes is about 20 to 30 milliseconds. So all of these systems, right, dysprosium and erbium, dysprosium-164 is going to be, seems to be the best, 150 milliseconds. This is, of course, of the systems that have been explored so far. A bit earlier on, or later on, I mentioned there are other systems, and the question is if you're courageous enough to go into that direction, like those that I list here. Chromium has been explored already. Dysprosium was deemed to be better, right? So these 3 have been explored in this vast literature now, or not so vast, but a good literature. And those are yet unexplored. If you're courageous enough in going to a complete new systems, you can try those. If not, based on what I know experimentally, the dysprosium-164 is the best candidate that we have now experimentally.
Thank you, Carlos. Any questions? I don't see further questions. So, Carlos, thank you once more. Let's thank Carlos again.
Okay, thank you.
If further questions pop up in your head, Carlos will be back with us tomorrow afternoon. So this ends our morning session. Please be back at 2 for an amazing lab tour.